mass flow rate of helium. The mass flow rate of helium lost to the atmosphere through the tube. B, the mass flow rate of air that infiltrates into the pipeline. And C, the flow velocity of the flow velocity at the bottom of the tube where it is attached to the pipeline. That will be measured by an anemometer in a steady operation.
Okay, thank you very much. Okay, so let's try and picture. We'll go out. I'll take us scroll back to the diagram and look at where it says A, the mass flow rates. Let's determine the mass flow rate of helium lost to the atmosphere through the tube. So which is the tube in question? This one, So the vent tube. So you have helium gas, okay, moving in this direction at this rate, 2 kilograms per second. Then you are venting helium through this tube that is 15 millimeters in length. So you have helium coming out there. So it's a breather for this helium gas. So as the helium is coming out, what's happening to air at 1 atmosphere? 25 degrees is also entering, isn't it? A part of that air is entering and joining this helium stream. The diameter of the pipe is 5 millimeters. So you're being asked to find the mass flow rate of helium lost to the atmosphere through the tube. So you're asked to find this rate, the rate at which we're losing helium through this vent tube. That's what question 1 is trying to ask you. Question 2 is asking you to find the mass flow rate of air that infiltrates into the pipeline. So you're supposed to find the rate at which this air is entering and infiltrating this pipeline. So that's mass flow rate. C is telling us to find the flow velocity at the bottom of the pipe where it is attached to the pipeline. That will be measured by an anemometer in steady state operation. So you're asked to find the flow velocity, okay, of this helium here, that point. So this is a solution here. So we have to make a number of assumptions for this. The pressure in a helium pipeline is maintained constant by venting to the atmosphere. So that's how the pressure is made constant, by venting into the atmosphere through a long tube. The mass flow rates of helium and air through the tube and the net flow velocity at the bottom are to be determined. Okay, so do you know that our foreparents actually understood this concept of venting and pressure reducing? I don't know if you're aware that actually our forefathers here in Africa actually applied this principle a lot. So what would happen even years back when someone has a headache? What do you think they used to do? I know maybe some of you know what they would do to reduce the pressure in the head or in the blood vessels around the head or around the forehead. What would they do? Those that know.
They would cut isindembo zija zanomenzochaya.
So what would that happen? Also, what would that make? I mean, what would happen after that? What was
blood? There would be oozing of blood.
Uh-huh.
Then the pressure that had built up in blood vessels will ease up.
And then what happens to how that person will be feeling? The patient?
The patient will feel better.
Isn't it? So it's the same thing here that's happening with venting. The same principle that happens with in this question here where they're venting a helium pipeline. Same thing, so they create another pipe where this helium is escaping a bit just to maintain the pressures in that main pipeline. The same thing that's happening here also actually. Okay, so what are the assumptions that you have to make? Steady operating conditions exist. Okay, so there's constant something. And helium and atmospheric air are ideal gases. Of course, in reality, but then anyway, for the sake of calculations, we take that assumption. And that no chemical reactions occur in the tube. So we're not expecting this air to start reacting with the helium, for example. We're not expecting that. So that's the assumption that we're going to take. And the fourth assumption is that air concentration in the pipeline and helium concentration in the atmosphere are negligible. so that the mole fraction of helium is 1 in the pipeline and 0 in the atmosphere. I hope you understand what this means. So it means basically that the air that enters into the main pipeline, the one that comes from the atmosphere and enters the pipeline, we're going to take it that concentration is negligible. Okay, so in terms of mole fraction, we're going to say that air in the pipeline is 0 and in the atmosphere is 1. Same as helium. Helium that leaves through the vent pipe, we're going to assume that it's 0, while the helium in the pipeline is 1. That's the other assumption. It makes our calculations much better. Okay, so number 2, the properties there, the diffusion coefficient of helium in air or air in helium at normal atmospheric conditions. That's a coefficient, or that's a diffusivity, 7.20 times 10 to the power negative 5 square meters per second. The molar masses of air and helium are 29. We know that 29 kg per mole for air, as well as 29, and then 4 kg per kilomole for helium, respectively. Analysis. So this is a typical equimolar counter diffusion process. So if you've noticed, what we mean here is that by equimolar counter diffusion process, can someone explain to us what this means in this case? So we said this is an equimolar counter diffusion process. Where is that counter diffusion process happening?
Yes, madam.
Yes,
So
please, Zachariah. Yes.
in this case, we have helium leaving the system
Mm-hmm.
and air entering the system. So the equimolar diffusion balance is at which the amount of helium leaving the system is equal to the amount of air entering the system.
Yes, exactly.
So
Thank
that
you.
balance
Mhm.
which should be equal to 0.
Yes, thank you very much. Exactly what we mean. Okay, since the problem involves 2 large reservoirs of ideal gas mixtures connected to each other by a channel, and the concentrations of species in each reservoir, the pipeline and the atmosphere remain constant. Okay, so we come to the flow area, which is the cross-sectional area of the tube. Remember, we asked to find the velocity in the flow area. Okay, so we're here now. Cross-sectional area of the tube, we get cross-sectional area of a tube which is circular, isn't it? Which is the same as the cylinder, which is pi d squared over 4. D there becomes the diameter of the tube. So we're given the diameter of the tube, this tube, which is 5 millimeters. So we convert that to meters, so it becomes 0.005 meters. The squared from the formula there, and our answer is 1.963 times 10 to the power negative 5 meters squared. Noting that the pressure of helium is 1 atmosphere at the bottom of the tube. Remember what we said in terms of molar fraction. Helium will be 1 in the pipeline and 0 outside at the top there, where the helium is escaping into the atmosphere. So now this becomes the molar flow rate. We use the same formula we used earlier on, except a bit different. So what do we have here? Coefficient diffusivity. We have our RT here at the bottom. And then what do we have? A, cross-sectional area comes in here. So this value multiplied by diffusivity. So diffusivity multiplied by cross-sectional area. This now becomes this part of the equation. Multiplied by this part of the equation, PA0 minus PAL over L, PA1 actually. So you have PA0, 1 atmosphere, isn't it? And then 1 there. So 1 minus 0 over the length of this vent tube is 15 meters. We've been given in the equation. So that now becomes our L that we're going to use here. So we have 15 meters here. So upon calculation there, we come up with our final answer. Therefore, mass for helium is equal to N times N of helium. And that's how we get this value that we found here, okay, which is this one. And then we're going to multiply it by what? The molar mass of helium, which we know as 4 kg, whereby for air is actually 29 kg. We looked at it earlier, this one. The molar mass of helium is actually 4 kg per kilomole. So that's a 4 kg per kilomole that we apply here. And this becomes our answer. So when you convert this one to grams per year, it gives us 0.5 grams per year. Here it's in kgs per second. When you multiply it, when you convert kg to grams and then seconds to years, you get 0.5 grams per year. So what is this? A part of the question. What were we solving here? According to the question, this was the mass flow rate of helium lost to the atmosphere through the tube. So this is the amount of helium that is being lost to the atmosphere through the tube. Quite minimal, so 0.5 grams per year. So every year, only 0.5 grams is being lost through that vent tube into the air. Okay, so coming to B, what is question B saying? Determine the mass flow rate of air that infiltrates into the pipe. Okay, so we've noted this. This is the equimolar counter diffusion. During an equimolar counter diffusion process, the molar flow rate of air into the helium pipeline is equal to the molar flow rate of helium. I hope that's clear. The molar flow rate of air into the pipeline is equal to the molar flow rate of helium, basically equimolar counter diffusion. And the mass flow rate of air into the pipeline is, so for air, just like we did earlier, that's negative 3 points. So remember, according to the principle of equimolar, remember here what we got was in the positive direction, isn't it? This value. But for air, because it's going in the negative direction, what happens? It becomes negative 3.85 kilomoles per second. Why negative? Because we say that in magnitude, they are actually the same in terms of magnitude, but direction is what is opposite. So when one is positive, the other one will be negative. In terms of magnitude, the value will be the same. The distance covered will be the same of these molecules during that diffusion. Multiplied by the molar mass of air, which is 25 kg per kilomole, and that becomes our answer there. Coming to the mass fraction of air in the helium pipeline, we use it via this formula. So we have that for air, which is what we picked here. Okay. Over the M total, so we're interested in finding the total molar mass. For us now to find the amount of air that entered this pipeline. And our answer is basically almost 5.6 and 10 to the power negative 11. That value is so small, basically equate it to 0, which validates our original assumption of negligible air into the pipeline. So basically the value for air into the pipeline is so minimal, we just basically equate it to 0. It's really, really tiny value. With what? How many decimal places? 12 decimal places. Then coming to the third question, the net mass flow rate through the tube. So net mass flow rate is basically what entered minus what left, isn't it? So that becomes molar mass of air, helium plus molar mass of air. When those are put together, we have negative 9.66 times 10 to the power negative 11, which is also a small value. So the mass fraction of air at the bottom of the tube is very small, as shown above, and thus the density of the mixture at x is equal to 0 can simply be taken to be the density of helium. I'll read that again. The mass fraction of air at the bottom of the tube is very small, as shown above, And thus the density of the mixture at x is equal to 0 can simply be taken to be the density of helium, which is, so this is the density of helium, P density is equal to P over RT, so we have the pressure there, and the R is temperature, so R is given there, multiplied by the temperature, which was given in the question, and that's the value we get. Then the average flow velocity at the bottom part of the tube becomes these values here. So you also have density coming in here, and that becomes our final answer. Okay, which is difficult to measure by even the most sensitive velocity measurement devices. The negative sign indicates flow in the negative direction, you can see. Okay, so I think for today we'll end here. There's so much information. I want you to just maybe look at these questions, examples that we've looked at one more time in your spare time. Look at them and try and understand them before we come to convective mass transfer. However, I think in our next lecture, I want us to solve about maybe 2 or 3 questions, exam type questions, under steady state conditions for equimolar counter diffusion, just to cement our knowledge there before we move to convective mass transfer. I think we can end here for tonight. There may be questions. I know there are probably questions, but I'll first advise you to go through this material yourself independently, try and understand, so that next week we bring our questions or we try and solve. Maybe as we solve other questions together, those questions that you may have for tonight may be solved during that.
All right.
All right, so we call it an evening. When is that? When is the assignment due?
You said 3rd April.
3rd April, which is a Monday, isn't it?
Yes.
Okay, so can we have that ready by Monday? All right, good night, everyone.
Good night. Thank you.
We'll meet next.
Thank you.
Good night, madam. Thank you.
Good night.